Good. So 3 points. The first is we need a picture. We have been doing some algebra, some calculations, but what's the picture that comes out of it? Okay? How do we connect these things that are in space with the ones in space-time that Etera is going to discuss? How do we connect these nodes, these quantum geometries with a graph and in an extended geometry? Then we go back to our cones, our conical defects and holonomies and fluxes. If you have done the calculation for the electromagnetic field, you have the advantage I worked out the simple case, and we're going to do the more complicated case. And this is something that is more technical, and we can then use discussion sections to go over the derivation. I'm not going to do derivations, but do ask if you have tried. Okay? And then the third part is there are computational tools, there are techniques. Pietro is going to assume that you know some of these techniques. I'm going to introduce just the minimum. If you have downloaded the notes and you have already looked at them, this third part is long. There's a bit of everything that you need to work with spin networks. I think I'm going to cover the first 2 pages of those 7 or 8, unless we have time. And the rest you can ask me. Okay? So, do you have your notes with you? You can download them, I see, and notate them. You don't have to copy. So the picture that Carlo was describing at the end of his lecture. Spin networks are states for quantum gravity. They provide an orthonormal basis of states of quantum geometries. They are labeled by a graph drawn here. You see a graph. There are many ways of thinking of this graph. One way of thinking of the graph is take a 3-dimensional manifold, chop it into cells. You can think of a triangulation or something even more general. It could be like really cells, like there's a word for this, it's cellular complex. Just divide it into chunks, and each one of these chunks has a neighbor, so you have to tell if one chunk is next to another one, and how many chunks do you have to pass to go back to the initial one. And the graph captures the dual of this decomposition. And you see that you have a blob, you have another blob, and if the two touch each other, then you can put a node in one, a node in the other, and a link that connects them that tells you that they are next to each other. So you can think of the graph as dual to a triangulation, dual to a decomposition itself. Graph. Then there's additional labels. There's spin associated to each link of the graph. And something we looked in detail is take a node of the graph with all the spins that enter at that node. And then at that node, you have to say how these spins combine to give something that is invariant under rotations. And we learned that the mathematical notion, a group theoretical notion, is the one of intertwiner, or of state in the Hilbert space in the tensor product of many spins that is invariant under rotations. Now, so last time we studied just one node. Today is many nodes. One node, we learned that if it's a node that is 4-valent, 4 legs, this is just a tetrahedron, a quantum tetrahedron. You can write a semi-classical state for a tetrahedron. You can write a state that is an eigenstate of the volume of the tetrahedron. You can write a state that is an eigenvector of the volume. You can write a state that is an eigenvector of some other observable, and therefore not of the volume if it doesn't commute with the volume. So one concrete way of thinking of what is this intertwiner is the intertwiner tells you this is a basis. This is not a general state. This is a basis of states. So it diagonalizes simultaneously a set of commuting operators. The operators are areas of interfaces between cells and volumes of cells. Okay? And so because of this, you get a picture. You have a state. You can think of it as a bunch of quantum polyhedra with neighboring relations. The area from this side, the area from the side is equal to the area from the other side because there's a spin per link. That doesn't mean that the shapes match. It's a quantum geometry. Or you can think of it as, suppose that I take a vector inside one tetrahedron, and I parallel transport it around. If I go from here to here, I don't know if it rotated or not, because I can only compare things when I bring them back. So from here to here, don't assign a meaning to this parallel transport. It's not unobservable. But if you go back to the initial place, you can ask, I take this vector, I rotate it, did it come out rotated or not? If it did, it means that there's some curvature. So this loop, if it's non-trivial, if the transformation is not the identity, then it means that through this hole, through this loop, there's curvature. And so this now doesn't focus on this geometry, on this polyhedra, but it focuses on the dual variable, the conjugate variable, that is curvature. Okay? You recall the connection is dual to the flux. You cannot diagonalize both of them simultaneously. And so there's a basis that is like the representation of the Q's. Basis is Fourier transform, the representation of the P's. Spin networks are a basis that diagonalizes the intrinsic geometry, these fluxes. Okay? There's another basis that diagonalizes curvature. That's not this one. Okay? I said lots of words. I should pause and let you ask. There's a question that I've been asked many times that should be raised, and it's not being raised. The question is, are we talking about space-time? Where is Lorentz invariance? Why are you talking about space? I thought we were doing quantum gravity, and you're speaking about geometry in space.
Okay, so I wanted to ask, you said that this network or graph is forming an orthonormal basis.
Yeah.
So there are lots of different graphs, each of them are orthogonal to each other. And my question is, you take one graph and you change just one link or add one node, just one small change. Is it still orthonormal to the original one?
Yeah, I'm gonna to address this carefully. The short answer is, if I deform the link without changing connectivity, this is the same graph, because I'm really thinking of the graph as a summary of the neighboring relations of cells. You know, you can. I'm going to make it more precise later. But if you change the connectivity, then it is orthogonal. If you don't change the connectivity, you just deform it without changing the topology, then it's the same state. And so if you want a graph, think of it as an abstract graph. Or if you want to think of it as an embedded graph, up with brackets around, in the sense of it's embedded, but there are equivalence classes, and I have to be precise on what are the equivalence classes. And the short answer is the equivalence class is essentially, think of the abstract graph. Okay? So where is space-time? And there was a question. I've been asked this question multiple times. You're doing SU2. Where is this SU2 coming from? This is spin. Spin, why spin? And Etera is going to answer this question. Not now in his lecture. But I think I should bridge, otherwise this question, if it's not addressed, then one cannot focus on this. So Carlo explained how to think of space-time as a process, as a transition amplitude from a state to a state. A transition amplitude, you can think of it formally as something that you want to make sense of the path integral with fixed boundaries, or as a transition from an initial graph to a final graph. And so this allows me to make a small immediate remark. That is, what is SU2? Why SU2? We know SU2 is the double cover of the three-dimensional rotation group SU3. And in space-time, we have the Lorentz group. How do you go from the Lorentz group to the rotation group? Am I doing something like I'm fixing a gauge, or I'm choosing things to simplify. I think the way to think about it is the same way Wigner teaches us how to speak about spin in a Lorentz invariant theory. You look at the Pauli-Lubansky form vector, you say, I have the Poincaré group, I have momentum, and I have generators of rotations, and then to speak about spin, I have to say, is this particle massive or not? Because if it's massive, you can go to the rest frame of the particle and define spin there. That's choosing a gauge. Or you can say, well, it's the norm of the Pauli-Lubansky for vector. So here, if each one of these is a tetrahedron or a polyhedron sets a frame. Polyhedron has a four momentum, or if you want a four normal. And so when you speak about Lorentz transformations of this object, spin is for a phase, but don't forget that this phase is the phase of something three-dimensional. And so if you want to speak about the spin of a phase, you have to say this is the spin in the frame. Or if you want, SU2 is the little group of the Lorentz group that preserves the four momentum of the tetrahedron. That for momentum for a particle, for momentum square is mass squared, minus mass squared with the conventions that the signature that I'm used to. And that is a massive particle, and this is a space-like tetrahedron. So this four momentum square should be minus volume squared. So that if this was a Lorentzian tetrahedron, if this was a null tetrahedron, would have a null for normal, a space-like. But we are doing only the space-like ones. Okay, and then what is that diagram? It's if you start from 1, you can have a transition amplitude to many, for instance, to 4. And this transition amplitude is the one that is Lorentz invariant. Yes, Daniel?
Yeah, sorry, can you elaborate a little bit more? What do you mean by the tetrahedron sets of rest frame? What do you mean by the tetrahedron sets a rest frame and has a 4 normal? I mean, we talked at length about, each face has a 3 vector normal. Yeah. Is there any relation between those? Or?
Yeah, good. So that's why I wanted to make this bridge. That is, everything that I did in the last lecture about polyhedra was background structure is three-dimensional Euclidean space. I never spoke about space-time. And so if you start on this fixed time slice, you don't have to think about space-time, you just think about three-dimensional normals. But if I want to translate all of that in space-time, I cannot speak about normals in space-time by themselves. I have to say more. In the same sense as if you have, we know how to speak about spin in relativistic quantum mechanics, but when you want to speak about spin in relativistic quantum mechanics or in quantum field theory, you have to first tell me how do you make sense of spin. You make sense of spin by saying this is a massive particle that has a four momentum. So something I'm not going to do is to do the tetrahedron and the polyhedron directly from the four-dimensional perspective. If I wanted to do it, I would either have to work with, instead of normals I would have to work with bivectors, or I can work with ordinary three-dimensional normals plus the four normal to the plane. And you see where all this confusion, this thing can come from. In 3 dimensions, a 2 form and a vector, they are the same thing. There's just an epsilon between the two. But in 4 dimensions, 2 form is equal to another 2 form. And so that's what's entering here. Yes, Carlo?
No. Since you, I think...
Throw.
I think those you were asking in which sense a tetrahedron fixes a frame. If you think a two-dimensional Minkowski space, a segment, a two-dimensional Minkowski space, a segment, it fixes a frame, the frame of the segment. That's it. So in 4-dimensional space, a 3-dimensional tetrahedron fixes a frame, the frame in which it, the 3-dimensional slice in which it sits. It's a space like. I just wanted to.
Good, thank you. Yeah. Okay, let's go ahead. So now, this is important. This is another point that is about. something Carlo mentioned about truncations. So I'm going to need things that come from here. I can put it back there. So let me connect this point to the action. The action for general relativity, if you write it in Einstein-Cartan variables, the variables are a frame that tells you the frame of a detector along a word line, and the connection gives you parallel transport. And at the same order, you see this one has one derivative and it's a 4 form. At that same order, there's another thing that is a 4 form. It has only one derivative, so it's allowed. If it's allowed, you include it. But if you include it, then you have to introduce a coupling constant. The Barberi-Mirzi parameter is the coupling constant. You can check dimensions, it's dimensionless. This is classically full general relativity. You can couple it to the standard model. We're just looking at pure gravity. Yeah. Now, compare this to the topological theory, the BF kind. It's called BF just because there's a B and an F, nothing mysterious, that Etera is going to describe in more detail later. They really look similar. There's an F here, there's an F here. Here there's this complicated thing that is a 2 form, and here there's a 2 form. So the kind of fields that you vary to get the equations of motion are omega is the same, but this one is a 1 form, and this one is a 2 form. And that changes the dynamics completely. Changes the dynamics completely in the sense that these two theories have a lot in common. They are both invariant under diffeomorphisms. They both are Lorentz invariant, internal Lorentz invariant. You see it in the fact that this is a Lorentz connection. But this one has an additional symmetry. If you shift the B field by a total covariant derivative of a 1 form, you see this derivative, you can integrate it by part and go on F, and that's 0, identically, not by equations of motion. Okay, because it's a double exterior derivative or something. This makes this theory practically empty. Now, all the solutions are solutions of the kind, the connection is locally flat, so you transport things and you come back and nothing happened, unless there's some non-trivial topology, and so you go around one big loop around some torus or something like this. So this one is empty, and this one is also empty because you can shift it. Okay? And so it has 0 local degrees of freedom. The only way to put degrees of freedom is some non-trivial global topology. So if you do it on R4, nothing, there's really nothing. This last symmetry is not here. The reason is that if you think of this as a form, a 2 form, it's not any 2 form. It's a 2 form of very special kind. There's this notion of simple 2 form. It's something that is the wedge of two things. If you do V wedge W, it's a 2 form, but not every 2 form can be written in this way. It can be written as a sum of simple 2 forms. This is of a special kind. It's E wedge G, simple, E wedge G with an epsilon, dual simple, but you get both of them. So sometimes to give a name to this thing, we call it gamma simple. No? And just by imposing that B is of this form, it gives you infinitely many degrees of freedom. 2 per point. Why infinitely many degrees of freedom? Well, first we know this is general relativity. If you do the canonical analysis, you find that we know it's gravitational waves at the perturbative level. Why that? Because you broke this symmetry. Now, this theory is very easy to work with. This one is rich physics. But the thing that you learn out of that is that you can really think of general relativity as this topological theory with the constraint that the B field is gamma simple. Okay? That B takes that form. So if you can impose this constraint everywhere, you unfreeze all of a sudden from 0 degrees of freedom, you unfreeze infinitely many. How do you do that? Well, it was clear. If B was free, it would impose that F is flat. Now B is not completely general anymore, and so it cannot impose that F is flat. It's not anymore a free Lagrange multiplier. It's a constraint Lagrange multiplier. Okay? So the constraint breaks the topological shift symmetry, this symmetry, and unfreezes infinitely many degrees of freedom. What do we do in loop quantum gravity? Which you can do it at the quantum level, but it's worth thinking about it first at the classical level, is imposing that this two-form is gamma simple. As it's a two-form, there's a place where it's natural to impose the condition. That is, if you are on a surface, imposing the condition on a surface, it's immediate because two forms integrate nicely on surfaces. So that gives you an immediate way of imposing the constraint in a controlled way, unfreezing a finite number of degrees of freedom at a time. You don't unfreeze infinitely many all at once. You say, start with the topological theory, then take your manifold, four-dimensional manifold, make a form in that manifold. A form is something that has bubbles and interfaces between bubbles that are surfaces. These patches, you impose it only there. You impose that the integral of the two form there, or if you want the fluxes, are gamma simple. You see what I'm doing? I'm saying the frame field, this is a one form. This is like saying lengths. And the point of view that we are taking is that two forms are more fundamental than one forms. Areas are more fundamental than lengths. So we are getting back lengths as composite objects by starting only from surfaces and areas of surfaces. Okay, so what's the picture that comes out of that? When you go from 4 dimensions down to 3 dimensions, you impose this constraint on a surface. When you cut the surface, you get a line that evolves in time. That line, you can think of it as a tube or many tubes. These tubes are defects, and they can carry curvature. So you can capture that curvature only if you go around a loop. And so what you have is essentially a new topological theory that now lives on this manifold that is full of defects all around. So you don't have to go all around the universe to find a loop that is non-trivial. Everywhere you can find a small loop that is non-trivial because it encircles some curvature. So this is standard general relativity, smooth curvature, and everywhere you take a loop, you get some curvature, and then you can shrink the loop to a point and define the Riemann tensor. And here you have many, many, many tubes in this room. I believe that in this room this is what is happening. No? There is a very small curvature that if I average of a wavelength of, it's a light year, then I will get something smooth. And you can think of it as many, many tubes, and you can capture the curvature of them by going around. Okay? What's the distance between the tubes? Well, the only way to read that distance is to read the dual variable, the fluxes. It's dynamical, the distance between the tubes. It's not fixed as a lattice. Okay? So in this way, you say, start with a theory with 0 degrees of freedom, and I add a few of them at a time. With finitely many degrees of freedom, the classical theory is completely under control. We know how to quantize a phase space of finitely many degrees of freedom, just ordinary quantum mechanics. And then the full theory is the completion to infinitely many. No? It's how you define any field theory. You don't define the field theory for infinitely many degrees of freedom all at once. To build Fock space, you do the 0 sector, the 1 particle sector, 2 particle sector, and then Cauchy completion. And here you do 0 defect section, 1 defect, 2 defects, 3 defects. Make it completely under control. You work out everything, and then you require that the limit is the limit where you take infinitely many with some condition, something controlled. Norms don't explode. Okay? And this concludes this first part, so should pause for questions. Yes, 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 1, 2, 3. And yes.
Is there any reason why you not start with dynamical gamma coupling in here? Because usually in QCD we start with the dynamical theta and then...
Can you say dynamical? Can you say more about what do you mean by dynamical?
I mean like, yeah, gamma to be like something that also like evolving through time.
I see, good. Yeah, that, gamma as a field. So let me connect it because you are saying a lot with two keywords. In QCD, in Yang-Mills gauge theory, people do something very similar. They say you have, for electromagnetism, the action is F mu nu minus 1/4. For Yang-Mills, it's just an abelian version. But then you say this one is gauge invariant and 2 time derivatives. How many other terms there are of the same kind? Well, there's at least another one. Epsilon mu nu rho sigma, F mu nu, F rho sigma. We should include also this one. But then you need a coupling constant, it's often called theta. And this needs to be measured. Okay? And how do you measure it? You have to find some observable effect. At the classical level, it has no observable effect. It's a topological term. But at the quantum level, it affects the electric dipole moment of the neutron. And so by measuring it, you can measure the value of theta. A bit in the same way as I was arguing before, that by measuring the spectrum of the area, you can determine gamma. Now, this measurement has been made. It keeps being made again and again. The measurement tells you that this theta, well, there's only an upper bound. It's small, smaller than 10 to the minus 20. And so then now people start wondering, like, is it 0? Maybe. Is there something that fixes it to be small? Like for gamma, I was saying the same. We don't know the value of gamma. Without knowing anything, one would say, well, it's going to be order 1. But we have to make a measurement and determine it. It's a coupling constant. The theory doesn't predict coupling constants. So for QCD2, people were expecting, well, theta is going to be order 1. Let's look for it. And now there's a question. Did we do the theoretical prediction wrong? Maybe we didn't. There's people argue that. But we didn't take correctly into account the non-perturbative effects. But at one loop, it looks like QCD predicts this effect for neutrons, this electric dipole moment, and the measurement tells you that electric dipole moment is compatible with 0. And so there's the next layer, that is what you were hinting to. The next layer is, okay, I want the explanation of why this coupling constant is small. If it's 0, is there a symmetry that sets it to 0? If it's non-zero but really small, is there some dynamical mechanism? These are the same kind of questions people ask for the cosmological constant. If it's 0, you don't ask. But if it's non-zero and really small in natural units, then I want to know why. The theory doesn't predict it. And so you can come up with mechanisms. And one mechanism is the Peccei-Quinn mechanism, where you say, well, no, this is actually a new field. It's another dynamical variable. And you have to look at the classical solution that it maybe environmentally or maybe because of some mechanism, it settles to a small value. Okay, so that is speculative in QCD, is one attempt. Like it's speculative in cosmology, why a cosmological constant might have a value. And here too, one can take that step and just extend general relativity and add extra fields. But I'm not doing it. So gamma is a coupling constant, it's not a field.
So I wanted to ask about the constraint and how you would impose it, because as far as I know, it is kind of, it's not imposed in a way as you usually would, as just like adding a term to the Lagrangian, and then you get the constraint. But is there a way to do that, or if not, how is it different to like other constraints maybe that you have?
Good. Let me separate classical from quantum in my answer. No? The classical level, if you want to go from general relativity, if you want to go to the from the topological theory to general relativity, you have to impose it. If you don't impose it correctly, you don't get back general relativity. So there are many ways of doing that. One way is, as you're saying, I put a Lagrange multiplier, and I put some version of, I don't know, b minus this squared, or some, there are more interesting ways, because after all, you just want to impose that this thing is gamma simple. So maybe if you put b squared, you don't have to put b minus c with g. That's what I'm saying. You can just say there exists some e such that. Yeah. Okay. Okay, now let me make one more step, still classical. There's nothing quantum in this step. They think of imposing the constraint completely in 4 dimensions to get back general relativity. That constraint, it is a bit ugly. It is complicated. No, it has to turn a trivial theory into a non-trivial theory. However, if at the classical level you do this cellular decomposition and you impose the constraint only on surfaces, then the constraint is way easier, because you're essentially imposing it in 2 dimensions and not in 4 dimensions. You're imposing it only on 2-dimensional surfaces.
And
okay?
that would already be not by adding a term, but doing it in this way that you described.
Yeah.
Yes.
And so when you do that, you don't go back to general relativity, you get back to a theory that is, if you want, a discretization of general relativity, or maybe better, it's a theory with finitely many degrees of freedom, where if you take averages over many of these degrees of freedom, you get back general relativity as an effective theory. There is a version of all these stories called the Regge calculus. It's not done in this way, but it's very similar. You do a theory where you do locally flat Christoffel connections with defects, and those defects are the cones. And people tell always Regge calculus as start with a triangulation, but if one reads the paper starts with cones. The paper starts, take a theory where you transport things around, and now I put singular points or cones. This is too difficult to do. It's better to break it by doing this, putting cuts. And then cuts become triangles, okay? Now, second part of your question was, in the quantum theory, do we do it right, do we do it wrong? Because there's a way to do it wrong, that is, I want to impose a constraint, but then I impose something else more weakly. And the proposals that are there are definite proposals for what is the vertex, what is this quantity here. To come up with that proposal, the proposal by itself is elegant, is some invariant of the Lorentz group. But to come up with that invariant, you don't take the classical theory and quantize it. There's no direct quantization in that sense. But there's a list of steps that motivate the definition. And so in that list of steps, one can ask, how am I imposing this constraint? Am I imposing it in matrix elements by looking at a subspace? Am I imposing it strongly on all of the space? It's clear that if you impose it too strongly, you're not doing the thing that I was arguing here, that you have to impose it only on these surfaces. Okay?
Okay.
And I guess Etera is going to do EPRL, and then there's going to be more details, and you should ask again. Yes.
Could you recall what is a defect, please?
Oh, I'm sorry. This was the first lecture.
Oh, I'm sorry.
There was the first lecture. So the short, check the notes.
Okay.
But the short answer is cones. You cut out something, you glue it back. This point here, the tip of the cone, that's what I'm calling a defect. It's no, because once you put it back, you cannot see anymore where the cut is. You can go around and I glue it. So the only point that remains is the tip of the cone. And sometimes I call it a conical point, sometimes I call it a conical defect, sometimes I forget conical and just say defect. Okay? And let's go ahead. Time is good. Time is good. Thank you, Francesca. Okay, you have seen already this slide, but I went through it fast. Let me do it once more, maybe more slowly, but instead of doing it more slowly, giving you more opportunity to ask questions. So, Ashtekar variables, before passing to defects, just classical, you start with general relativity, formulated in this language. And you see here there's this two form, the area to form. We want to find the variable conjugated to the area to form. When you do a foliation, as I was saying before, it's foliation in space, but also you have the four normals that are the internal frames. And so you go from E capital I, that goes from 0, 1 to 3, to small I, that is 1 to 3. Okay, I've already separated the 0 part. So these are areas in space. And the question is, what is the conjugate variable? As when you do a particle, you get Lagrangian equal PQ dot minus Hamiltonian, PQ dot minus Hamiltonian constraint. And so when you do that analysis, you see that the Q dot is the identity of omega is the same omega component small I, small j, so just the spatial part, plus gamma Kij, I have to say what I mean by Kij, and Kij are all the components of omega. Now, how do I get something with two indices? Omega, I already took omega small I, small j. What there's another small I, small j? There's no 0, 0 because it's antisymmetric. There's a 0 I, but that has only one index. This has two indices. How did I get something with two indices out of one with one index? But it's a vector. If I take a derivative, I would need a covariant derivative, but I don't have a connection yet. Levi-Civita, where is it? Levi-Civita, thank you. In 3 dimensions, this thing happens all the time. You can think of a two-form or the dual that is one vector. Ij, epsilon ijk gives you a thing k, and you can do it the other way around. And so if you want, this is the component space, space. This is the component one space, one time. Here there's a 1 over gamma that I put out, so I have to pay it. It's a gamma here. This combination is the one dual to P. Let's give it a name. Ashtekar connection. Okay, that's not the way it was originally derived, but it's not historical derivation, but it's to me the fastest derivation. No? And you see I shortcut the derivation by a lot, but not going through the full Dirac protocol of how you go from Lagrangian to Hamiltonian, taking account everything, because I just want the symplectic structure, just want this. So I just have to check where are time derivatives. Here, there is only one time derivative, so I just have to bring out the one time derivative. If you want to do it more carefully, you need lots of paper and lots of patience, and do it at least once. And so now you give a name to this, E, name to this, A. You see that there's a factor in front of it, and so when you ask what is conjugated to what, you find that A is conjugated to E. In fact, A is conjugated to E over 8 pi g gamma. You take it from here, you move it on the right-hand side. As Carlo was saying, this is like the mass. Momentum is mv. You can take m and you move it on the other side, and you say Poisson bracket of x with v is 1 over m. Cosmologists always do this thing when they do cosmological spacetime. They bring out the scale factor instead of keeping it in the momentum. Okay. One more step, then I'll let you ask. We learned that out of the connection, you can compute the holonomy. We learned for the electromagnetic field that out of the electric field, you can compute the electric flux. And then I left you with the exercise of compute the Poisson bracket of the two and show that it's the holonomy again. Now, here there's one more step in the calculation that is, this is non abelian. There's this index I that is an index of SU2. And so you have to keep track of that. When you take the derivative, it brings down a Pauli matrix. Pauli matrix enters just in the middle, so it splits. Do I have it? Yes, I have it. It splits your link in two parts, where the surface cuts the link. You also have to be careful. If the link goes this way and the orientation of the surface is this way, that is normally in the same direction, then you get a plus. Otherwise, here you get a minus. So if they don't intersect, 0. If they intersect in this way, you get a plus, and if they intersect this way, you get a minus. Connection with connection, 0, so holonomy with holonomy, 0. And then there's the third one that can be puzzling if you say, I did the electromagnetic case. Electric field with electric field commute. So flux with flux commute. So what was all this story about the group SU2 where you have the fluxes that have the SU2 algebra? And that takes a little bit of thought, because one has to realize that to do the non-abelian flux, you cannot do just the non-abelian flux of the electric field. You have to transport around the electric field. And when you do that, they don't commute. And I'm going to address this in a moment, because it's important. You don't find it always explained. So I'm going to go there, but I should pause first. Hans.
Okay, so I never understood why do we need to add to the action, to the general relativity action, the term with 1 over gamma. Never understood it completely. Basically, it's maybe because when you when we go on with the calculations, we obtain a term like PQ dot. We obtain.
Yeah, good. So why is it there? What if I didn't put it? I didn't think about it, I didn't put it. So 2 steps. If I didn't put it, none of what I said would go ahead. I wouldn't get any of this. If I don't put gamma, if I don't put the term, let me see if I can say it right. You can do the canonical analysis, and in the canonical analysis you would find the triad is conjugated to the extrinsic curvature. If you have studied ADM, intrinsic metric is conjugated to extrinsic curvature. And the story ends there, and everything is correct. There's no of having a gauge theory. Extrinsic curvature is not a connection. Extrinsic curvature is not a one form. You cannot integrate it over lines. You would get essentially only this term. You see there's a gamma out, gamma and gamma cancel. This one, gamma to infinity, disappears. So you get k, and k is not a connection. What is a connection is omega. So if you want a theory of fluxes and connections, you need gamma. If you don't put gamma, you get a theory. It's not a theory of fluxes and connections. And am I making a claim that the theory cannot be quantized? No. I'm just making the claim that people have tried and not succeeded. It might be that one tries and finds a way of quantizing metric-based or length-based quantum gravity. Here one is I'm taking the point of view that area is more fundamental, that loops are more fundamental, and this, you really have to think of it as this is the key ingredient. This is the statement that the fundamental degrees of freedom or geometry of gravity are loops and fluxes. Does nature do that? We don't know. That's the thing that we have to go and check and find. And so what is the thing that distinguishes loop quantum gravity from any other theory of quantum gravity? What is the one statement that if we didn't have loop quantum gravity and you had told that statement, then you can rebuild everything from scratch, is loops are fundamental. That's why it's in the name of the theory, loop quantum gravity. Once you know that, you know the fundamental degrees of freedom, and then you can build the theory. You could have done length quantum gravity, and I don't know of a full construction of the theory. You can put it in quotes, as I was doing with the path integral, but then you want Hilbert space, you want observables, you want spectra. And I'm not saying that it cannot be done. I'm saying that this proposal has been around for long, and it has never reached the step of being sufficiently concrete to extract concrete predictions comparable to this. Does nature behave like that? Well, that we have to test. We have to go and look. Okay? So that answers the two questions. One is, why can I do it? There was one more question. Why am I allowed to add it? So this is an important separate lesson. It's the lesson of all effective theories. That is, what fixes Lagrangians? One would say nature fixes what is the Lagrangian. But nature fixes the physics at some scale, and then you can ask what happens at other scales. The theory is a classical theory. That first line is not look quantum gravity. One is the effective theory for planets, for cosmology, for black holes at large scales compared to the Planck scale. And so the standard logic is assume symmetries, assume field content, write the action as an expansion in number of derivatives, including everything that is allowed at that order, and coupling constants are to be measured. And so by not putting it, you're just making the statement that the coupling constant sets it to 0. But actually the coupling constant needs to be measured. Electromagnetism, if you don't put this theta term, you're not doing really electromagnetism. You're just assuming that it's 0. Okay.
Okay, thanks.
1 and 2. Daniel.
Yeah, can you just comment on how constraining is it that in this canonical analysis you have to have a 3+1 foliation to go through the theory, because that presupposes that you have global hyperbolicity, which then in turn also just fixes the topology of your spacetime. So, I mean, are these like global Cauchy surfaces that have to you assume asymptotic structure and they extend all the way out to I0, or can this just be done in any arbitrary compact region of spacetime? Is this better addressed in the covariant formulation of spin phones?
Yeah, good. So first point is the topology of spacetime is fixed. Manifold is not dynamical. I did declare the fact that I'm fixing something. I'm not doing a theory of quantum gravity where there's a sum of topologies. At least here we're doing one thing at a time. Fix the manifold, fix the topology of spacetime, and then you sum overall geometries. Okay? And so you're adding, well, you didn't just fix the topology. You really asked that you can foliate it with Cauchy slices, and yes, it is an assumption. Can one relax it? Well, yeah, that's one more step. Okay, that one can do later. Do I need to do it space-like? Well, we are trying to build a theory in the most ordinary way of associating the Hilbert space initial conditions on a spatial slice. There are other things that can be done, and often need to be done when you want to do general boundary compact surfaces, as Carlo was describing. Okay, so take this as a guide to get to the quantum theory, but then one has always to do the reverse. Once you have the quantum theory, then this is the zero order check. Do you recover back this one or not? Okay. Yes.
I want to say one more thing about this extra term. I was thinking that we put it because we can put it, because it disappears when you go back to classical picture. So I want to ask, are there other possible terms to add there that disappear when we go back to classical picture?
Yes, there are others. There are other topological terms, but they don't affect this one.
Okay.
Okay. And yeah. Okay, let's go ahead. I do want to clarify a bit this. So, holonomies. This is a one form. You see there's a sigma Pauli matrix, 2 by 2 matrix. That means I need a part order exponential. I cannot do the integral. The integrand at different points in the path don't commute. I need a part order. If this doesn't encircle any cone, any conical defect, any curvature flux, then this is trivial. So how does this depend on the path gamma? Well, you can deform the path gamma as you want as long as you don't go across a defect. No, you can move it around. So it has all the nice transformation properties. It's not just gauge invariant because you went back to the same point. If you take a trace, it's gauge invariant. Otherwise, it transforms nicely, it tells you the rotation between two. If you take a trace, this is called the Wilson loop. People in lattice gauge theory use this. They build the theory out of that. But they do this path that have an extent, have a lattice spacing. Here there's no lattice spacing. How do you know how far they are, two of these tubes? Well, you go to the dual variable, the flux. Flux through which surfaces? You can do any surface that you want, but you want only you want to find the non-trivial ones. If you do the flux through a bubble that doesn't contain anything, it's like doing a Gauss law for something that doesn't contain any charge. So let's take a few of these defects. So the picture was in space-time, it's a foam. You slice it and you get tubes. These tubes can branch, and so you can get a surface that tends at 3 tubes. And now you can compute the flux through this surface. But to compute the flux, you want to integrate the electric field through that surface. But the electric field, you cannot sum something here with something there. There's no way to compare something here with something there. You have to parallel transport it to compare it. So the way you do it is fix a reference point. Do a parallel transport from the point where you're integrating to this reference point, this h minus 1, and then you integrate. And now you have introduced so much structure that one would say, well, here you put A and D I read. Here you put an I, sigma I, so this is a 2 by 2 matrix, and this is a 2 by 2 matrix, so still good. Here there's a surface, and here there's a surface. But here it looks like there's a lot more structure. There's a point that I'm integrating over. There's a path. Does it depend on that? And the answer is no, because inside here there's no defect, and so that holonomy is trivial. It's just a trivial locally flat holonomy. So it doesn't depend on the path. And then does it depend on the exact surface? If I deform a bit the surface, if I inflate it and I make it come out a little bit on this side? Well, it's the same, because it's just capturing the same flux. Okay? So I can deform them as much as I want, as long as I keep them attached to the same structure. And now you can do...
Sorry.
Yes, yes.
I am a bit confused about both the definitions, because the holonomy is trivial. I mean, if we don't consider a defect, only on the equation of motion of BF, not in general. So we are considering those quantities only on the solution of the equation of motions for BF theory.
Yeah, I generally call them differently. I think of equations of motion as the one that give me the time evolution of dynamical variables, and then the ones on BF. It's true, I get them as I vary the action, so when I vary the action, I get equations of motion, but they are so trivial that they are really just constraints. They're just the statement that the connection is flat. And so there's no real distinction between, generally we make this distinction of, are you speaking on shell or off shell? Are you making a statement that makes sense only on the classical solutions or in the full quantum theory? For a topological theory, there's no distinction between the two things, because these are simple hard constraints that if you solve them at initial time, you have solved them at all times. Equations of motion are things where you choose conditions freely at initial time, and then you can ask if they are preserved or not. Constraints are not like that. Constraints are things without the time derivative. Okay? And so if the complaint is, well, but wait, yes, the theory tells you that you can deform it only on solutions of the constraint, yes, I agree, and I'm saying that's the only thing that there is.
Okay.
Okay? There is no off-shell in a topological theory.
Okay, I see. And the second question is, why I cannot just integrate the two form over the surface? Why I need parallel transport to define it? Because if I have a two form is defined on the whole space in principle, so I just don't need to fix the electric field in a point and just parallel transport. I have all the, let's say, vector field on the whole surface.
Yeah, so this is important to absorb this. This is often missed in presentations, and people drop these two pieces as a simplification that then ruins everything that comes after, because this is really important. The message behind that is, if I have a vector and another vector, what's the sum of the two? And the first time one learns vector is, well, the sum of the two is the sum of the two. It's this one. vector, vector. But then you realize that there you really added a structure that is non-trivial. That is, I have to take this one and bring it here, and if everything is flat and I do it just what I'm doing, then I can sum vectors. But when you learn differential geometry, you learn that you cannot sum a vector with another vector at another place. You can only make sense of, take a vector, transport it to the same point where this vector is, and now you have a tangent space and you have the structure to sum vectors. Here it's the same thing. If you want to take this that transforms as a vector, an SU2 vector, and do the integral is just a sum. You cannot sum a vector here and a vector here. You have to take it and transport it.
Yeah, and I see the point, but it's not a vector, it's a two-form. Two-form are usually integrated over two surfaces without the need of parallel transport.
This is a two-form manifold internal vector. Two-form internal vector. You cannot, I'm speaking about this one.
Yeah.
I'm not speaking about this one. This internal vector, you cannot sum it at different points. It doesn't make sense to sum it at different points.
So it's like a coefficient for this two form?
It's a two form with values.
Yeah. It's an SU2 value two form.
Okay,
you cannot integrate an SU2 value
maybe
two form.
We can discuss later about that.
But this is really, really important, often underappreciated. And if one misses that, as it's done everywhere, because they just put here, they put alpha, they do alpha I, EI, then you have to assume that that alpha transforms, and you have to make it into a dynamical field and not a. If you don't realize that, then this one doesn't make any sense. Flux with flux gives back flux because A with V don't commute. Flux with flux. In electromagnetism, this one is 0. You have to go on a billion to make it non-zero. Yes.
I miss how did we go from having defects to defects being able to connect. I missed the geometrical.
Let me understand. Say more. Add some things that I understand.
So I lost the picture, the geometrical picture. So you were saying that you have the conical defect, and that gives you curvature. But I don't know what happens when two defects merge.
I see. Yeah, now I understand. Yeah. So I told you only about if they were infinitely long. If they are not infinitely long, if they have this structure, I think it's fine. Good. If they are not infinitely long, then you can still go around a loop. You can still ask, if I go around this one, what happens? And you can move it, but you cannot go from this to this other one. So the mathematics of all this is take a manifold, cut out the network of defects, and look at the pi 1, at the first homotopy group, and representations of the first homotopy group are the dual graph to the cellular decomposition. Okay? And then there's the pi 2, and it's these fluxes. Okay? So now you were also asking, what happens here? Well, I could modify the theory in such a way that something happens there, but there would be additional ingredients. All of the condition is that nothing happens there. Or if you want, if you look at the magnetic flux through here, there's a conservation of magnetic flux. This is automatically encoded into these rules for the fluxes. Yes. You have to check the time. We are good. One more question.
Could you repeat why why imposing simplicity constraint implies that defects are possible? So from the BF theory side, how these defects emerge and why there are no defects in pure BF theory?
Yeah, it's clear. Thank you. So you can think of BF theory as all of this where there are none of these defects, so that all these loops can be shrunk to a point and they are trivial. So there's only one loop, the trivial loop, unless there's some big non-trivial topology that is like one cosmological scale defect, like the universe is a torus or something like that. And these things, these surfaces, the only way that you can do is to close them into balls or into things without a boundary, and once you do that, they don't encircle anything, and so just by Gauss law, they are zero. And so topological theory essentially tells you everything is zero unless some topology of the manifold is non-trivial. Now, how did I add the defects? There is something that takes a bit to see, that is, I started from 4 dimensions and I went to, and I'm telling you the 3-dimensional version. In the 3-dimensional version, the most immediate way of looking at it is if you do the abelian BF theory, this is just like force-free electrodynamics. It's electrodynamics with no charges, no magnetic fields, and no electromagnetic waves. And then a defect is just a solenoid. And so you can go around the solenoid and capture the flux through the solenoid. And this one is the electric flux through these solenoids that have a magnetic field that has a conservation law. And so from this point of view, you can think of all of this as just postulated at the 3-dimensional version. You can postulate the classical phase space and the quantum Hilbert space as obtained by taking, first you go down to a BF theory, 3-dimension, and then you put by hand these defects. Now, the point that I was making earlier is you don't have to put by hand these defects. If you start from 4 dimensions, you do cells in 4 dimensions, and you impose gamma simplicity on the boundary of cells that are areas. Those are 4-dimensional defects, and you can go around a 2-dimensional thing with a loop. And when you slice it, you get this one. And to explain that, one has to really go through the construction of spin forms. That, I shortcut a lot in one slide. Okay?
So in principle, one can start just with ordinary BF theory and think about these defects as modification of topology of the initial slice by adding non-trivial Wilson line.
That's the fastest way of.
Okay, but this has nothing to do with simplicity constraints then?
Yeah, that wouldn't have anything to do with simplicity. Correct. But once you have that A and D are conjugate, that comes from this canonical analysis, and so in a sense it knows it, because I'm saying the interpretation knows it, that A is the Ashtekar connection, and D is the area flux, knows about the simplicity constraint. That's what I'm saying. So you can shortcut it, but to have the full picture of why everything fits together, one has to start from 4 dimensions. Good. So 25 minutes left. I have to do one more thing, that is the basis, the spin networks, a bit of technical details of hard work that one needs to do before one can do computations that Pietro is going to present. So part 3, spin network basis states. I said gamma JI, that's a lot of information all at once. So there's a lot of material in here. I want to cover 2 points. What is a graph and what's on the links of the graph. So this is a graph. So I need a bit of names. I want a directed graph. You can think of it as a set of nodes and links with properties. What are the properties? The properties are that links are a map from node to node. There's a source of the link and a target of the link. Okay? And by doing this, I have the graph. You can think of it as a matrix where each entry is a node, and the matrix has an entry that is 0 if that node is not connected by a link. No, component ij, this is the adjacency matrix. By the way I'm describing it, I'm describing only a directed graph. And so a link is an ordered pair. Now, often one needs more structure, so let me comment on that. So this is an abstract graph. There is no embedding into a manifold. There is no notion of the dimension of the manifold. There is no notion of the topology of the manifold. There is no notion of, is there a knot in a link? Because it just tells you there's a source, there's a target, and there's a link. Why this is the relevant notion for us and not paths in a manifold, like embedded graphs? Because by what I was telling you before, I can move these paths around as long as I want. Nothing changes unless I do something topologically non-equivalent, that is, I cross one of these defects. If this is a graph that goes around this loop, to go around that other one, I really have to break it somewhere. So what I need is just take this decomposition into cells, build a graph that is dual, that is, you put a node in each one of the cells, and a link between two nodes if the two cells are adjacent. But where do you put the node? Nobody knows. It's not important. Where do you put the link? It's not important as long as it connects them. So you can put all this redundant information and say, I put it, but then I don't care. Or take directly the point of view of, this is an abstract object, it's a directed graph. There is one more thing that I have to address, that is, I have to give you an example first. Valence is what one calls, like I have a node, how many links come from that node? So valence 4 would be like a tetrahedron, valence 6 like a cube. A complete graph is you put nodes and you say everything is connected with everything. Can I have it as a decomposition of a manifold? That would be a very weird thing, like every cell is neighbor to every other cell. Well, we are doing quantum geometry. It doesn't mean that every state has to be very similar to a smooth classical space-time. Something that is dual to a triangulation looks like this. No? Just each cell, you describe it with the, well, each triangulation, we describe it with the dual graph. That's the way to say it. Now, often you're going to see that you have a cell, you have another cell, and there are multiple links from one to the other. Like you can think of, take a tetrahedron, another tetrahedron, you glue two faces, and then you glue the two, and all four of them. So it's two tetrahedron with all the faces glued back to back. It looks weird, no? But you know, it doesn't have to be flat. This is curved. It's like triangle, triangle, and then I glue also the other, glue also the other. But now there's something to address, that is the definition that I gave here doesn't allow it, because the definition is a link is a map from a node to a node. But now you have, there are four of them here, so how do you deal with that? Well, you just say, well, here actually there's another node, it's bivalent. Okay? That's the way to make the formalism work quickly, and you always have things that are just directed graph. Okay? Now that I have the notion of graph, I go back to group representation theory. You can do all of tensors and all of group representations by writing lots of algebra and infinitely long formulae, or you can learn how to do diagrammatics, and you start only drawing these tracks and curves, and Pietro is going to have 18 slides of diagrams. Each one of those diagrams is an extremely long formula, but once you learn how to translate tensor contractions and group representations into diagrams, you don't have even computations. You just draw something and you say, well, this drawing is equal to this other drawing, and it's way faster than doing a long algebraic calculation. The only disadvantage of that is that it becomes very difficult to communicate with people who don't know that diagrammatic language. But that's the only disadvantage that I know. Then you have to translate it. Okay? So what is this diagrammatic language? It's a matrix, has two indices, so it's a line. Okay? And the trace of a matrix has no index. It means you take an endpoint, you take the other endpoint, you glue them, and so it's a circle. So let's see how to do that. I assume that you are familiar with all this. Is that right? That's right. No. You have a group, you have SU2, you can do a rotation as a 2x2 matrix, you can do the unitary representation, and then you can do the unitary representation spin J, and this is a Wigner matrix, M and prime. You can think of it as the matrix element of this thing between J and prime and Jm. Okay, for me, for us, for everybody who works with it, is this. It's a line with a blob that tells you, so first it's a matrix, so M and prime. One is down, one is up, so there are arrows. There's a label here, G. It tells you, you take something here, you rotate it by G, you get something else out. Okay? What's the inverse? Change the arrow. Where is J written? I should have written it here. You have to put J, otherwise the symbols, the things don't tell you the representation. Okay? You know the notion of a character. Chi j of G is defined as the trace of dj of G. If you don't, well, it's a standard notion. So what is that? Well, it's you put a blob and you close the line. Okay? And then lots of the rules, like, you know how annoying Wigner-Eckert theorem is the first time you learn it? In diagrams, it's just you have to close a line and you just have to check how it closes. That's all. There's no theorem to prove. Okay? Who did this, who invented this? Was so many people independently at many times. Sometimes for tensors in differential geometry, it's called Penrose rotation. For group theory, I don't know. The Russians, there are full books on group representations, like Warszalovich. It's all about representations of group. And you go through it, and there are no formulas, they're just diagrams. There's a beautiful book of Pedrag. It's all about group theory. All of group representations, all done with, it's called Bertracks. All are in terms of diagrams.
The best place is probably Halagar's thesis.
Halagar's thesis, yes. Yes, and Pierre-Martin Dossau's introduction. Yeah. Yes. We should share all this material. We can put it. There's a lot more, yeah. Yeah, this is a good recommendation. Take any thesis of anybody who has worked on quantum gradient and look at the appendix. Everybody has worked out these things and maybe ended up with some slightly different notation. So let's see if I can turn this graph into a formula. There's an intertwiner, there's a link, there's a group element, and here this is the group representation, if you want, the Q Schrödinger wave function for the spin network state gamma ij. The one that before I was writing gamma jlin. This is in the group representation, okay? So wave function. So how do you do that? Well, this is the diagram that you're going to see in Pietro's lecture. So for each link, I had to write a Wigner matrix. There are four Wigner matrices from 1 to 4. For each node, I had to put an invariant tensor. When you put the invariant tensor, you have to be careful that the indices contract correctly. And here there's J1, so this has to be the invariant tensor between J1, J2, J3, and J4. And has to be the one that has the indices up. And then the one on this side has to be the one with the indices down. Then you have to make sure that you put them in the right order. And then you have to make sure it's all written in there. Okay? And we studied these ones last time. These are, you can think of them as eigenstates of the volume, basis of eigenstates of the volume, and they are tensors. Today I told you about these ones. You put them together and you get spin networks in this representation. Okay? And often one doesn't write any of these things, but if you have to write the code, you write this and then you make the step of turning each piece of the diagram into code for a calculation. Okay? Yes?
Simple question. I want to ask about the direction on the link. What does this direction represent?
Lower index, upper index.
The
You-
arrow on the link is
Yeah.
the index?
No, it's not the index. It's are you doing G or G minus 1? So you're taking something and you are rotating it. So what side are you taking and where are you rotating? It's a path. So you can really think of it as there's a cell here. I take a vector, I parallel transport it from here to there. Okay? And then if I want to come back to check if there's curvature in between, I have to come back in the other direction. So these ones are oriented all in going that direction. So to go the loop, to do the Wilson loop here, to do the check the curvature, I would have to do one going that way, one coming back, and that's that character that I was saying before. Okay? And it takes time, and it takes time also to understand what notation everybody is using. My recommendation is come up with your notation, and then you make a dictionary. It's the easiest. Like here, I'm not putting a plus. Some people put a plus. For me, this I make it planar, and I read all of them counterclockwise. And then you have to be careful. And Pietro tells me, oh, but there's a sign you're gonna miss, and so be careful. Yeah. So he's gonna. So and as usual, sometimes you just want to prove relations up to overall signs, and so you don't care and you just go through. Sometimes you really want to be careful because you really need that, because you can have, interferences. Samart.
Yeah, so I wanted to make sure I have the correct physical picture here.
Yes.
So each of those intertwiners, that is a tetrahedra.
Yes.
And the links are just their, essentially the faces. And so what this diagram is essentially saying is I have two tetrahedra, and all four of their faces are connected with another one.
Yes.
And then, it's done in a kind of non-trivial way because we have a group at each link.
Yeah,
That's what's
and
going
this
on.
group at each link means to go from one tetrahedra. If you have just two tetrahedra that touch each other, you have a vector in one, and I want to know how to transport it into the other. And so that's why I need a group element, I need a parallel transport. And if I go here and I come back the same way, nothing happens. But if I go from this phase, but then I come back by another phase, then I'm doing something like this, and then coming back by this other one, and now I can get some curvature.
Okay.
Okay? That's a loop.
Yeah, just to add on that, I guess maybe it's hard to try and picture curvature off of multiple tetrahedron, but if I go down to, let's say, a triangle,
Yeah.
and I have two triangles, and all three of their edges
Yeah.
are connected, that seems like a pretty degenerate triangle to me.
It is. It is. So instead of taking two triangles and attaching all the edges, try with 4 triangles. And so you get some curvature at one tip. You get a tetrahedron, but seen as just the boundary of the tetrahedron, not the.
So
or think of a sphere with many triangles.
Is this specific example kind of
Degenerate? Yeah, it's simple because I can write everything. But is it interesting? Well, sometimes it's good to look at it. No, it's like the first non-trivial case. It's like dipole.
Yeah, so the example you were giving before, you have 2 triangles and you glue them along their edges, okay? And then was telling
Yes.
this trick. You have both of them glue them, and then you make a sphere.
Yes.
So you have the simplest triangulation of the surface of the sphere, in which all your edges are on the equator. Yeah. And then this is just one-dimensional. It's the simplest triangulation.
Exactly. So you see that there's a curvature because it's a sphere. It's a lot of curvature. The Euler theorem still works.
But then the triangles themselves would not be flat.
Yeah. Good. 10 more minutes. How much can I cover in 10 more minutes? What do you need? I don't need more than that. No? Do you need this one? Oh, yeah, yes. You see? Okay. Okay, let's do one example. Okay? It's simpler than the one that I was giving before. Take this graph. Sometimes it's useful to have a name, theta graph, because it looks like a theta. Okay? Take this graph. It has a node, it's trivalent. So it's not even a tetrahedron now, if you want. It's a tetrahedron with a face of 0 area. But the other three don't have 0 area. Can you picture it? Something. Okay? You have it? No? Well, you have to keep the order, so you have to elongate it so that you send the base to 0 and the sides fixed, so it's very long. It's a needle. So very degenerate, but after all, it's an example. Now, if you need some non-trivial example, take 5 tetrahedra and glue them as the boundary of a trisphere. It's this pentagram that you're going to see in many places that Pietro and Etera are going to discuss many, many times. So very degenerate, but it's just an example. So 2 things connected in this way. So I should illustrate a few properties. First, there is this notion of gauge invariance, or Gauss law, or if this is a triangle, if this was a tetrahedron, the sum of the normals has to be 0. But the normals are fluxes, the normals are angular momentum. The sum of them being 0, it means, I explained it last time, that this is a tetrahedron up to rotations. Up to rotations means up to SU2 transformations. Up to SU2 transformations means gauge invariant. Gauge invariant means that how do you act here, here, and here? Well, there's a group element here and here and here. So as Carlo was explaining, it's like saying I multiply the group element to from the source, from the left, with the group element, and if I do it, nothing happens. That's gauge invariance. And if I do it at the other node, so if I put a group element at each node, and I make a transformation of all the links at that node, nothing should happen. This is the requirement of gauge invariance. Can we check it? So that's the example that should help with some of the machinery. Let's not do it in complete generality. Let me put here spin 1/2, here spin 1/2, and here spin 1. Okay? So now you have this spin network that is intertwiner, intertwiner, 1/2, 1/2, 1. And can you tell me an example of intertwiner between 1, 1/2, and 1/2? An invariant tensor that has 3 indices, 1 of spin 1 and 2 of spin 1/2. Sigma. We did it. Right? Now we use it. Sigma. Put a sigma here. Then you need another sigma here. Am I forced to put sigma? No, you just have to choose an intertwiner. But it happens that for trivalent it's unique up to a scale. You normalize it. So sigma here, sigma here. How do you put the indices? Well, you have to put them so that they contract. Sometimes matrices help. So there's a sigma, there's H1, then it is another sigma, and then there's H3, and then it is another sigma. So I'm going around and I have to contract it, so there's a trace. And then there's a spin 1. Spin 1 means that the I and J are contracted with a Wigner matrix in representation 1. It's generally called just a rotation. So rotation Ij. And this one is Wigner matrix in representation 1/2. That is just the fundamental, and so I'm not even putting. So this is D matrix 1/2, and this is D matrix 1. So I've given the spin network, yes.
So if you go in a circle, you have to go like for H1
There is an H3 inverse, and you're right. Thank you. And check also the others. This is the kind of things that it's important to put the arrows to check them, because then you write the code and nothing is working, and then you realize that you put the arrow wrong, right? And okay, good. So let me say it again. How do you prove this gauge invariance? Well, here this was the example with 1/2, 1, 1/2. If you want to be more general and put J1, J2, J3, then we know the unique intertwiner is the Wigner 3J symbol, okay? And when I was saying what is the definition of intertwiner is, it's a tensor that if you rotate all the indices at once, it remains itself, okay? It's the way you say also the, what is the Minkowski matrix. Minkowski matrix eta mu nu is the tensor that if you do the Lorentz transformation on all in the indices, becomes eta mu nu back. It's the definition. Eta mu nu is the bivalent intertwiner of the Lorentz group. Okay? And this is the trivalent intertwiner of the rotation group. Now, how do I say that same thing diagrammatically? I have a point, I rotate, and that's equal to no rotation. Or if you want, you can take this one, bring it through the node, but when you bring it through the node, you have to reverse the arrow, so it becomes G minus 1. G minus 1G is identity. You see, I don't have to prove anything anymore. You have a blob, I can move the blob through the node, I have to take into account that the arrow reverses, and so they cancel. And so every time you have G, 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 and a node and everything going in, it's like putting on G. That's the definition of intertwiner. That's what I was saying. There's lots of long calculations, and once you have a notation, if you want, or diagrammatics that encodes all the properties, then you're not really doing any more calculations. You're just drawing things and proving theorems just by drawing them. Is there more than you need? Okay, I did put sketch of the proof of that same thing. It's a page, but it's the same thing of the diagram of before. When you have time, you go through it and then you ask me. We don't have to do this in class. And yeah. That's all. Thank you. Back at 11 sharp.